All right. You see I just opened the text. This is our new chapter, chapter 9. This one is the one of the longest chapter, with a later chapter on calculated two variables later on. Okay, but this one is long, and then say this is one of the hardest of the two chapters in this course for this semester. Okay, it's about sequence in series. Okay, so there's 9 sections. See, usually we only have 6 sections or something, but this is 9 sections. All right. So we'll talk about first about what you call sequence. Okay, so in our daily life, the term sequence series is basically the same, right? But in mathematical terms, especially in this course, we will distinguish between series from sequence. Okay, so this is sequence. Sequence always means infinite. Okay, so it is just A1 to A10. So you stop at 10 terms, then it won't be a sequence. Okay, so sequence must be something that we can write A1, A2, A3, A4, then comma, dot, dot, dot. It continues indefinitely. Okay, so that's what we call a sequence. We call it a sequence, but we really mean it as the infinite sequence. Okay, and how you write down the sequence? Well, you can write down something like this. Just write down in longer terms. I write a couple of terms, first term, and then dot dot dot. Okay. Sometimes you write this down as you see this braces. Okay. A1, AN, and runs from 1 to infinity. That's something. Or sometimes if it's clear enough what the index is, and you just with the bracket AN. Okay. Okay. Now, sometimes you write down a sequence by a formula. Okay. So this is the nth formula of the sequence. Sometimes you just write down the term of the sequence. First 1, 4, 7, 10, 13, dot, dot, dot. Or you can write down a explicit formula. Looks like this one. For example, this one, 3n minus 2. So that means for n equals 1, you get 1, 1, so 1. Okay. N equals 2, you get 6, 4. So basically it gives you this the sequence here. Okay. Or you may use what we call recursion formula. Recursion means that how you get n term from the previous one. Okay. So for example, the nth term is the previous one, add 3. Okay. And you start with the first term is 1. So the A2 here, n equals 2, that means A1 plus 3, that means 4. A3 is A2, which is 4, plus 3, so they make it 7. Okay, so again, the sequence here can be described just using explicit formula, or we call recursion formula. Okay. One example that you might um, uh, you know the term, but let's see if you have see if you recognize this one. Okay, so the nth term is the previous one plus the second previous. Okay, do you recognize the sequence? So in this case, just start with one. Say start with one, and sorry, let's say you need two data. So A1, A2 equals 1. So, right? So you get 1, A2, A2 is A1 minus nothing. So just 1 because it's given. All right. And the third is A1 plus A2. So this is 2, right? So the next one would be the sum of 2, 1, so 3. Okay. The next one would be the sum of this 3 and 2. This is 5. Next is 8. Dot, dot, dot. All right. Do you recognize this kind of sequence here? You recognize the name? Anyone? Have you uh, ever heard this name? Fibonacci?
Oh, yeah.
Yes, that's the last two terms. You add them last two terms always. Okay, so that's Fibonacci. Okay. So this is what we call a recursion formula. Explicit formula, recursion. All right, so for example, this one is explicit formula, 1 minus 1 over nth. So if you list them, a few terms, this. First one is say, n equal, so 0 is you cross it out with 0. We start with 1, just give you 0. Okay. For a equals 2, 1 minus 1 half, so there's 1 half that you get always. Or the second example, you get also this explicit formula. Okay, this is 1 minus 1 to the n. So nth is a odd, even, odd, even, odd, even. Takes turns. Okay, in turns. So you get sometimes it is plus, sometimes it is minus. And we add it to 1. So sometimes it's slightly below 1, and sometimes it's slightly above 1, right? So it's like, well, you start with 0 and then start there like this. Okay, so we call this a it's not alternating, but oscillating. Okay. Oscillates, not zero, what do you call it? Oscillating near 0. Okay, so this, or you may have also this one. Okay. Okay. Or this one is just a constant sequence. So the n is 0.999 regardless of n. Okay, so start with this. Just keep repeating on and on and on. Okay, so convergence is about limit. A sequence converges to number L if L is the limit. The question is, how do we compute the limit for this discrete thing for sequence? We used to do the limit for numbers, sorry, for functions. How we compute limit for sequence. Okay, so I skip this part. And just compute sequence just like usual. I'll show you later. Like this. Progress limit of sequence, just regular properties. Okay, let me show you how to compute this one here. Um, okay, can you see the notes now? One note?
Yes, sir.
Okay. Remove my keyboard. Okay, so in this case, uh, remember the trick that I mentioned maybe last week or so, that you try to identify what is the value, and then try to factor those out. Okay, so n is large because n going to infinity. Okay? So 3n squared is large, 7n squared is large. Okay, so the thing is the bad terms, so we call bad terms, is the n squared because that's the largest one. Okay, so you try to factor this out. So n squared. So what's left is just 3. Okay, and you also factor the n squared out from the denominator. So what's left is just 7 plus 1 over n squared. Okay, so I would say here factors, factor out vector, identify the vector first. Okay, now with this trick, um, factor out the vectors, then you just cancel. So what's left is just constant 3, constant 7, and you have this one. But this is 1 over large, so this is small, it's going to 0. Right? So you're left with just 3 over 7. Okay, so this is one of the effective method how to compute limit without using L'Hopital. Of course, you're using L'Hopital, but the thing is rather awkward because this is no functions. This is sequence, and sequence there is no graph of functions. See, if A is the derivative, then you can take derivative of functions, but there is no derivative of sequence. So better write it complete. Cannot use. I would say directly. Indirectly, yes. What I mean directly. Okay. So in this case, L'Hopital is not applicable. Okay. All right, let's move it again to the textbook. That's the easy part. All right, so this is exactly what the thing we did with factor the n square and then cancel up and both the numerator and denominator. So it's like this. Okay, so this limit theorem. All right. So if that is a something like ln over e to exponential, right? So let's do this one. Okay. Here's the key idea here is that, well, if you compute how you compare limit of sequence and limit of functions here. Okay, so suppose you have some that looks like this one. Okay, and if the limit functions is equal to L and then the sequence is also L. Okay, so in this case, you just pretend this is not ln of n over exponent n, but think of it just pretend this is just ln of x over e to the x. Okay, this problem here. And because x large, so ln of x is large, and e to the x is large. So this the large over large. Okay, so it's justified to use a L'Hopital here. Okay, compute the derivatives. This is 1 over x. This is remain e to the x. All right. So what about the limit? As is x is large. It's 1 over x going to be 0. Then e to the x is, well, this is going to be large. Let's see. Yeah. And small over large is small. Let's give you 0. Okay, so then by L'Hopital, you get this limit. Okay. And because you know the limit of the function is 0, then the limit of the sequence is also same 0. Okay, so you just pretend this n is just x and compute using the, and you can compute a lot of things because the law of limits, how to compute limits, applies for n also for sequence, like squeeze theorem. Okay, just like this one here. So just pretend let's do this one. Now let's pretend this is just x, not n. pretend the function should be sine 3x over x. Okay, and we compute this limit. Now we have a sine x is between -1 and 1, right? So if you power 3, okay, and then put this absolute value, so we don't have to deal with -1. There we go. And if you divide this by x, well, we are mirroring this one. So you get just 0 versus just 1 over x. Oops, inequality. 1 over x. Okay. And if you take the limit, this one goes to limit x goes to x getting larger. So you have this one, this limit. Less than this limit, because this is by squeeze theorem. Squeeze theorem. Okay, so this limit here is squeezed between 0 and 0, so this should be 0. Then this limit side. Okay, but this is not the original problem, because the original problem without absolute value. But the thing here is that if you have the absolute value equals 0, then the without absolute value is 0. This is property that we use. So we just state it as a fact. This absolute value is 0. Then without 0, it is also true. Okay. All right, so let's continue with this one. This means that, with absolute value that's 0, then it is also true for without limit, without absolute value. Okay, and therefore, okay, this is the last conclusions. Now this is not A. Yeah, okay. Turn this to parameter n. Okay, so this is how we use the L'Hopital in this case. Let's go back to this one. There, this is one. So with absolute value equals 0, then without absolute value is 0. So, all right. What we call a monotonic sequence. Monotonic sequence is something like a sequence which is always increasing or always decreasing. So it looks like this one here, right? So this is always increasing sequence. So this is monotonic sequence. Monotonic sequence means that the nth term is larger than the previous one. Okay. So this is what we call increasing, because it's getting larger and larger. So this usually for n, say, okay. So this is the monotonic sequence. All right. And the important thing here is that if we have a monotonic sequence and bounded, then it converges. Okay, so let me write this down because this is important fact. All right, so let's see. Increasing means that, say, A1, A2, A3, or AN is larger than the previous one. Okay, so this was called monotonically increasing. Okay, so now the theorems. So I don't know how we call theorem the P, maybe because they be in the order. Okay. Uh, so if let's say we have AN is increasing and bounded from above, then it converges. Okay. So we'll see one example. This before we stop. Example. So this is the idea, the picture here. So you have an increasing sequence, keep increasing, but it is somehow it has a ceiling. Okay. So the thing here, because it's keep going up, but the ceiling prevents it going up, crossing the ceiling, then it should converge. This should converge. Okay. All right, so uh, sequence Bn n square over 2 to the n. Let's show this one converges. Example. No, it converges. Okay. So let's see here. Let's list just the observations. Okay. So we try to list the sequence, the terms of the sequence. So plug in one. If you have one and then you have 1/2, right? N equals 2. N equals 2, you have uh, 4 over 4. This is 1. Okay. And n equals 3. That is 9 over 8. Okay. Then 4. 4 is 16 over, again, that's 1. Okay. 5. And 5 equals 25 over 32. And so on. So you see, looking at the terms, it is difficult how to show this is it converges because we cannot predict what the limit is. Okay, so we turn to the problem here. What the term is. Okay, so we show it is. We will show this one. Uh, Increasing, not for a larger n. Okay. See, see, n bigger than 3. Okay. So you see. So start from here, going there. Okay, so start from n. All right, let's compare this to the so it's n squared over 2 to the, write down like this. A n plus 1 is n plus 1 squared to the n. Uh, so what we have is this is n squared plus 2n plus 1 over 2 to the n plus 1. And we write this down as n squared over 2 to the n plus 1. Sorry. 2 to the n times, let's see. That's how to do this one. Okay. And take it out. Uh, this. Okay. All right, so write this down like this one. Okay, so what we have here is that uh, this is an times let's see, this is 1 half. Seem to forget what to do. Um, Let me show you this later. This one though. This one is, I should give a note to this one. Okay. But otherwise, you can do this one. So let me just do this in later. So let's think this way. X is x squared 2 to the x. Okay, and we'll try to compute, uh, show this is increasing. Is increasing. X greater than 3. All right, and using derivative, use derivative. Okay, so let's see, f prime. Okay, f prime is, see what you get here. So just derivative of this one. So 2x times 2 to the x minus, let's see, x squared, derivative of 2 to the x. So that's ln of 2 times 2 to the x over 2 to the x squared. Okay, then show this one is positive. Mm, oops, I should stop in 2 minutes. Let's see why this one is larger. X is minus X. Positive, positive out, minus there. Okay, We'll check it later. This one is increasing, actually larger. Okay, then this is positive. Okay, so F is monotonically increasing, and therefore uh, the sequence n squared 2 to the n is increasing. Okay, and let's see, this is bounded. Say by 2. Okay, so by increasing and bounded, so the conclusion is that uh, this one converges. Okay, all right, so I'll stop here and then let you get prepared to the to log into the LMS. Okay, we'll continue this tomorrow with the series. We'll have some more example and then start with series. All right. So good luck. I'll see you then tomorrow. So I'll end this. Stop sharing and then stop recording.